without further ado, I give you Jack Dongarra, University of Tennessee.
Thank you so much. Yeah, so, well, let's see. So it's the University of Tennessee in Knoxville, Oak Ridge National Laboratory, about 40 miles from campus, and then the University of Manchester, about 4,000 miles from Knoxville. I don't go there every day, but occasionally I do. So I'm going to talk about some issues related to hardware and how they're affecting our computing today, and also looking to the future for computations there as well. So it would help if I plug this in. Oh, come on. Okay, so this is the list of the top. This is the top 10 of the top 500 computers. There was a session last night. If you missed it, I'm going to go over it very quickly. So this is the #1 computer, the fastest computer. That's fastest as measured by running something called HPL, or the LINPACK benchmark. And it was built by the people at the National University for Defense Technology. Today that machine was moved, or this past few months, it was moved from that university over to Guangzhou province, and it's in Guangzhou City today. It's called the Tianhu 2, Milky Way 2. It's based on Intel parts, so they use Intel Xeon processors, plus Intel Phi accelerators. So think of a node being composed of some number of those, and then they're going to build up a system based on those nodes. This machine has 3 million cores in it. 3 million cores in it. The commodity processor has 12 cores, and the Phi has 59 cores, the way I count cores. So from that, they build up their full system to 3 million. So 3 million cores. The other thing to keep in mind is each of those cores, if you want to get good performance, you need 4 threads of execution. So that machine, we're talking in excess of 12 million threads of execution, have to be maintained to get reasonably good performance on that machine. And that's today. This is not future stuff. That's today. Okay, they achieved 34 petaflops, 34 times 10 to the 15 floating point operations, 64-bit operations. An operation is an add or a multiply. 62% of the theoretical peak performance. Peak performance, you go out, look at the cores, look at what the cycle time is, calculate how many operations you can do per cycle, and that gives you the number. The power consumption, 17.8 megawatts. 78 megawatts. 1 megawatt per year in the U.S. is $1 million. So to turn that machine on, about $18 million just for the power. Just for the power. That's going to be a big deal in the future. This is the efficiency, flops per watt. So it's about 2 gigaflops per watt. That's where we are today, 2 gigaflops per watt. For exascale, we have to get to 50 gigaflops per watt, and that's going to be a big stretch getting to that point. And then you can see the remainder of the list. Oak Ridge has this machine. It's a Titan. It's Nvidia. Kepler is the power horse for that machine. 16-core AMD processor plus a Kepler. 500,000 cores, the way I count cores. That's not CUDA cores, that's real cores. 192 CUDA cores equals 1 core. That's, the streams of threads of execution there. 17.6 petaflops, about half the performance of the Chinese machine. 65% of the theoretical peak. This top 10 list, the only new machine from last time is this machine here in Switzerland. So that's the only new entry on the list. That's a Cray machine, uses Intel and Nvidia parts in it. And they achieve, modest 6 petaflops worth of performance. Okay, so what do we notice? A lot of cores, a lot of core counts pretty high on all these machines. Power consumption's pretty high, over megawatt is what we're talking about. And machines use accelerators. So there's 4 accelerator machines in the top 10 list. And we'll see what that means in terms of the overall list itself. So if you take a look at accelerators, going back to 2006, and count the number of accelerators in the top 500 machines for each of the editions, you get this interesting situation. Today, if we look at the number of accelerators, it's at 53. So 53 of the 500 machines use accelerators. And that number did not change since last time, since June. So I'm surprised at that. I don't know if you are. There's a lot of hype about accelerators here, and only 53 machines have them. That says something. And Nvidia has the highest share of those machines, right? There's a few There's 13 machines using Intel's processors. There's 2 using AMD's accelerator, and the rest are Nvidia. And a number of countries have invested in it, and that's the story. The other part of this is, if we take a look at the performance and which fraction of the performance is coming from accelerator-based machines, that's told in this story. So think of it like this. Sum up the 500 machines and get a number for the performance for all 500 machines. Sum up the performance for those accelerators, and then compute the ratio. 35% of the 500 machines, 35% of the performance of the 500 machines is based on those 53 accelerator machines. So they provide a tremendous amount of computational power according to the top 500 list, right? So that's an interesting thing. This is looking at, again, think about summing up this list, and look at where we get half of that performance. So where do we get half of the performance of the list? Today that number is at 17. So 17 machines provide half of the performance of the 500 machines, right? So it's a low number. So we got to, if you take a look at how they're distributed, you end up with this graph here. So here's the 500 machines on the top 500 today. We have one machine which is tremendously powerful, a couple that are close to that, half of that, and then really drops off rather dramatically. So just a very few machines have that high performance capability. Okay, you probably know this story. The way things work today, at least on the systems here, we have a host processor. That host processor has some memory. We have an accelerator. In this case, this is a Kepler processor. It has some memory as well. It has a floating point execution rate, 1.3 teraflops for that version of the Kepler. The host processor is rather modest, 96 gigaflops for the theoretical performance. You program this machine by having your data here. You think about taking data, moving it over to the accelerator across this link here, doing the computation over here, and then passing data back over to the host processor. That's sort of the standard flow of execution. You want to get as much computation as you can from this part of the machine, right? This link here it's a DMA link. It's realized through a PCI Express bus, and that bus has a rating of 1 gigaword per second. So the transfer rate is 1 gigaword. The performance over here is 1 teraflop. That's 3 orders of magnitude difference. So if you move data over here, you got to get a lot of operations out of it before you move it back. If you move something over, do one thing and move it back, you're dead. The performance is going to be driven by this number here, and it's nowhere near going to get anywhere close to that peak performance. So that's going to be the struggle, if you will, the challenge of using this architecture. And the way we do this today is we don't think about putting one of those accelerators on. We have a board, and that board may have 2 socket chips and maybe 3 accelerators. So we have a machine in Tennessee called Keeneland. It's based on Intel parts. It's manufactured by HP, and it has three of Nvidia's boards, on each of its host board, and we drive that computation by programming across that. So you're going to be writing a program that sort of controls this, and writing another program which sort of controls this. That's the way life is. This is the top 500 list again. We're looking at the efficiency of the 500 machines here. So the first thing you should notice is no machine is greater than 100% efficient, right? That's a good thing. But there's other effects that take place here. So we see these stripes here. What are these stripes about? How does that affect what's going on? Well, that set of machines, the blue triangles there, those machines are based on gigabit Ethernet interconnect. So that's a very, very slow interconnect. Poor bandwidth, high latency. Those guys lowballed their computer. They buy commodity processors and they buy a very slow commodity interconnect. And they end up with performance that's on the order of 25-30% of peak performance. Right? So you probably wouldn't want to do that if you're serious about high performance computing. The blue dots are machines which use 10 gig Ethernet. So they've invested a little bit more, and they get more return, about 50% of the performance on LinPack. and the accelerator machines are given by those triangles. So we see a scattering of them, but again, they're not at the top end. They're not extracting the most performance. They're not seeing efficiencies in the above 80% for the accelerator-based machines, and that's primarily due to that link, that connection between the part there. It's driving down the performance. You have to pass data across a very slow link, and that's retarding the overall performance of the systems. We're interested in designing software for these machines. We're interested in designing linear algebra software. We want to look at replacing the software that's in LAPACK and ScalaPACK with a design that effectively can use those architectures. So that's where we're coming in and thinking about the retooling. So the software that we've developed has a long history. We can think of it going back to LinPACK. LinPACK was designed in the 70s. There's two people within 10 feet of where I'm standing who designed and built that software. Cleve Muller's the other guy. So that was based on vector operations. It was a Fortran implementation. It produced state-of-the-art algorithms. It implemented them. The numerics are just terrific. However, performance is not so good on modern architectures. A lot of data movement goes on in that. It used level 1 BLAS, so a lot of data traffic with the level 1 BLAS. In the 80s, we redesigned that software. That software was designed around blocked algorithms to effectively use the cache, the memory hierarchy of the systems and try to minimize data movement. So these algorithms do pretty good on some of the shared memory machines as well. Low-level parallelism was okay for those architectures. ScalaPACK took these ideas here and pushed them forward to a distributed memory configuration. Message passing goes on inside of ScalaPACK. So you could put together a machine with 3 million processors, run the ScalaPACK code, and get pretty reasonable efficiencies on that kind of architecture. But it requires you to reorganize the data. That's one of the issues there. Today we're working on packages which extend it, let's say, to go to hybrid architectures. So one of the packages we're working on is called MAGMA. MAGMA is the package which allows us to use multiple GPUs on one shared memory address space. So the stuff I'm going to talk about is shared memory address space. We're going to distributed, but that's where we are today. MAGMA is targeted for Nvidia stuff, for Intel stuff, and also for AMD stuff. So we're targeting for all the machines. We want to write portable code, or as portable as we can. So we're trying to design things in a way that allows us to do that. This is with colleagues at Berkeley, my colleague here, Julian Langou, at the University of Colorado, Denver, and a bunch of our former postdocs at INRIA, France, and Bordeaux, and also at KAUST in Saudi Arabia, are helping with this effort. Okay, so this gives you a rough index as to what's available in MAGMA today. This is today's version. There's CUDA, OpenCL, and Xeon Phi versions of the linear systems, eigenvalue problems. And then we've developed some specialized routines that do multiple precision. They use single and double precision to extract more performance. All of our routines go through a testing apparatus. That testing apparatus comes from LAPACK. So we're trying to at least be at the same level of numerical accuracy, I'll say, that we had with the LAPACK code. We don't want to lose that. And there's Linux, Windows, and Mac versions of some of these things if you really wanted to. At some point, all these dots would be filled in, but today that's the story for MAGMA. It's a project which is continuing as we go along. So in some sense, we're trying to extend this historic path here and develop software that looks at multi-core and software that looks at hybrid and multi-core, heterogeneous systems, allowing us to have access to that library software. The algorithms that we have in LAPACK exhibit the following kind of processing. We're going to do an LU factorization of a matrix, and we're at some stage of that factorization. The next thing we do is we take a panel from the matrix, this green panel, and think of introducing zeros in the lower trapezoid. So we're going to construct a set of transformations that do that zero out that, and then we're going to apply those transformations to the rest of the matrix. That's sort of the flow of the algorithm at this stage. And the first part is to do a triangular solve with this triangle from the factorization, and that rectangle. So we do that. That's a parallel operation. And then we do a matrix multiply, a rank K update to this green part of the matrix. And that's also a matrix operation. I can get very good performance out of this particular operation. It has think of it as order n cubed operations, matrix multiply, order n squared data movement. And that's what I want. That's what I need for that kind of architecture where we have a very slow link between them. And that defines a step. So in some sense, there's a sequential part and then a parallel part. There's a fork join mechanism going on in that algorithm. Bulk synchronous processing. Think about running that algorithm on a machine which has 1 million cores. So we're going to be running 1 million here. That's good. But over here, we're on 1. That's going to kill us. You can't do this. Your performance just goes way down. That's the end of parallelism, if you will. So this is a repeat of that concept. Fork join parallelism going on for various steps. When you take a look at the profile of this, when run on a 16-core processor, it has the following characteristic. Think of time evolving, and think of tasks that are being executed in the parallel and the sequential part. Colored is good. I'm doing productive work. I'm getting something done. I'm accomplishing the factorization. If it's white, the processor is idle. He's waiting for work. So you see that fork join parallelism. You see that sequentialization that occurs at various phases as we go on. So the performance is not too good for this particular algorithm. What I'd like to do is to squeeze out that white space as much as possible. So we want to design an algorithm which can do that. We want to get out of this fork join model of parallel processing. So what we do is, as soon as possible, we start on the next step. We don't wait for the whole block to be completed. We don't wait for this whole operation to get started. As soon as we get enough information, we engage in the next step of the process, sort of overlapping, sort of looking ahead, doing things maybe in an out-of-order sequence to allow us to get our computation done, but doing it in a way that it still retains the numerics of the problem. And we continue that, of course. And what you end up with is a directed acyclic graph model of the execution. The execution begins, and as soon as possible, it allows other things to begin based on the data dependencies of the task. These are not new ideas. This is a data flow model of a computation. People have done this for a long time, but we're implementing this today in our modern software to try to extract performance, to try to break that bulk synchronous processing that goes on. So we're going to be doing that with these hybrid systems. We're going to be looking at it in the following context, trying to do the sequentialized bits on the host processor, try to give the GPU as much work as possible, that matrix multiply to do before we go on to the next step. At least that's the first implementation I'm going to show you. So as a directed acyclic graph, we've designed a runtime which basically takes that information, the tasks and the dependencies, and executes them on the given machine. So basically, think of your program now as in two parts. It generates tasks and another part that executes the tasks. Think of the generation part as your algorithm itself, and then the runtime system, perhaps it should be part of the operating system, takes those tasks and executes them respecting the data dependencies that are in the task itself. So we've designed a runtime system that goes along with the numerical library. It's called Quark, and it does that feature of executing that directed acyclic graph. So it takes the tasks, executes them, has a pool. It has a little knowledge about what the critical path is in the graph. In order to get the most out of the parallelism here, we would have to examine the graph, get the critical path, execute the critical path that frees up the maximum amount of parallelism in that graph, and then execute it according to that, respecting that. So when you do this, when you have that runtime system, when you describe the algorithm in terms of a directed acyclic graph and you run it, you change the execution flow. This is the execution flow in the conventional way, fork join parallelism. you change it so that you can compress out a lot of that white space, and the time to solution now can be greatly reduced, minimizing things, doing things in sort of an out-of-order fashion, unrolling these loops, and allowing the computation to flow in a much better way. So that's sort of the structure that we're going for, both with plasma and magma. And if you're looking at it from the coding side, this is a high-level description of the algorithm that we have. It points to tasks that have to be done, and it describes what's the inputs and outputs for those tasks. The data dependency graph needs just that information. What's the input? What's the output? When the outputs are ready, then perhaps the next task can be run. That gets translated into a program which explicitly says this is a Quark call to this routine, and then passes in information that deals with the data itself. So it can analyze the data and do the right thing. So that's the Quark implementation. And again, at a high level, we have the CPU, the GPU. We're going to be sending things back and forth. So there has to be that kind of coordination that takes place. We're going to factor a panel on the front end, on the host side, and then the back end is going to be done on the GPU side. That's the first implementation. So here's what that looks like if I do the implementation. So this is the flow of execution. Time is flowing this way. The top thing is the host processor. That's the guy who's doing the sequential part of the computation. And the way to read this is this box here is doing the panel. The purple thing is transferring data over to the GPU. The GPU then works on that and then passes information back to the host, and then the host starts up again doing the next panel. And that's sort of the flow. That's the first version. No overlap was done there. That's the bulk synchronous processing implementation. If you think about unrolling it one step, you end up with a graph that looks something like this, just doing one look ahead. So as soon as we can, we start the next block, allowing that CPU to do something, and then the GPU is busy doing things. Notice the GPU is pretty busy all the time. We've got plenty of work there, pushing it off. The CPU is the idle guy in this case. We're going to continue doing that unrolling step, doing more and more things, getting ahead of ourselves so that the CPU can do active work and that the GPU can be kept busy doing that. But we still see white space here. So in order to get rid of that white space, what we have to do is to steal some work from the GPU. So we're going to do work stealing is going to take place from the GPU to fill in some of that white space and allow that CPU to run in parallel fully with the GPU. And you got to be a little bit careful that you don't give the CPU too much work, because it'll stall the GPU then. So that's sort of the trade-off there. And when you do that, you can effectively implement and run this thing so that you can fully utilize both the GPU part of the machine and the CPU side of the machine. And when the execution flow of that looks something like this. So this is on a Fermi processor, one Fermi board, and that's on a Kepler. You can see the difference between Fermi and Kepler quite clear. This is the performance where you don't do this overlap. The CPU is not engaged in the computation, and this is when the CPU is fully engaged. So that's the benefit, if you will, by engaging the CPU. CPU is much lower performance in general than the GPU. And the same thing is true of the Kepler as you go out as well. So we have a board which has one socket, commodity, and then 6 Nvidia cards on it, and we've done experiments with it, and this is the performance we see in that case. So again, we're able to fully keep those 6 GPUs busy with the computation. At the beginning we can't. We have to get something started, kick-started, and then once that happens, we can pretty much keep the GPUs and the CPU occupied for most of the time. There is a little white space that's going on there, and perhaps we can tweak that to get a little bit better, but the performance is getting pretty good at that point. And we see this kind of graph going on this particular architecture. This is a symmetric positive definite matrix. We're up to about 5 teraflops on that particular thing. It's about 6.5 teraflops peak performance for that board. And the same thing is true for QR factorization. And this is a positive definite, again, doing it on a Fermi board, the performance is lower. This is on a Xeon Phi. The same software can be run on the other architecture with just modest changes. The user isn't even aware of the changes associated with that, and giving us a fairly good performance level. Okay, so that's the end of my talk. It's time to rethink our software given the architectural trends that we see. Very disruptive in terms of what goes on, and everything has to be rethought and rethinking. You know, today data movement's very expensive. Floating point operations are cheap. Our machines are over-provisioned for floating point operations. Major challenges ahead. You know, we have to think to billion-way parallelism. We've got 12 million right now, and we're going to be going to billion-way with the exascale machine. Many issues there relating to faults, relating to power, and we need to really make a big investment and to get the new technologies. So some of the software is available. You can go to the website and pick it up. Be happy to answer any questions if I have any time left.
You do have time for questions.
Excellent.
So do we have any questions here in the theater for Jack?
Do you think there's potential in the next 5 or 10 years for machines in the top performers to be using technology that bypasses the interconnect with on-package or on-die accelerators?
Right. So the big issue here is we've got this very slow link, PCI Express, between the two parts of the machine. What about changing that architecture, maybe more integrated into the chip itself? So the future, if I were going to predict the future, I would see a chip which has everything on chip, but it has heavy cores and lightweight cores. The lightweight cores would be the similar thing to what we have in our Nvidia card, and the heavyweight cores are the things that we think of, all of the wonderful cache and instruction look ahead and all the other things that cost so much on our commodity cores would be in that part of the chip, and there would be a stacked memory. So information doesn't have to come from the edges of the chip. Information is going to flow directly into the processor through the chip. So 3D stacked memory, you can see examples of them out here if you wanted. So that's coming. Then we'll have optical interconnect between things, not copper paths, but optical interconnect. Again, you want to minimize the amount of energy that's going on with this thing. The power budget, you got to get to 50 gigaflops per watt. You can't do it with the technology that we have today. All of these things help in minimize reducing the power that needs. The fact that we have 3D things minimize it. The data paths are shorter. You know, a floating point operation is taking on the order of 10 picojoules to execute. So that's the energy necessary to fire that floating point operation. To move data from DRAM over to the part of the machine where you're going to execute it takes on the order of 2,000 picojoules. So that's an enormous amount of energy that's going into the data movement. So you want to shrink that as much as possible. Stacking and having things travel through the vias is certainly the way to go on this thing.
We have a question from the online community
Excellent.
as well. So the question is, do you anticipate any changes to LINPACK to reflect changes in the latest workloads?
So do we workload to reflect workload? So that's a loaded question. Let me rephrase it like this: Do you intend to change the benchmark that's used to measure the performance of machines from LINPACK to something else? And the answer is we want to augment the data that we have from LINPACK. LINPACK benchmark, the top 500 has been around for 20 years. It's a tremendous and valuable amount of historic information there about trends and the direction of computing. We don't want to abandon that. But it provides, LINPACK, the top 500 benchmark is being used today to drive the architectural design for future systems. And that's probably not a good idea, because solving dense matrix problems are not really the core thing that's done on our top-end systems. They want to solve large, sparse matrix problems that are going to be solved through an algorithm which does some kind of iterative technique, and we want to design a benchmark that more fits into that space. But again, I don't want to throw something away. We're going to collect both the LINPACK stuff and also perhaps this new benchmark, which would look at not a dense problem, but a sparse problem, solved using a sparse method.
And one more question here.
Thanks. In the example that you showed, there was a fairly straightforward pipeline where you could partition things early, and if you had multiple cards, you could send everything down to each one regularly. do you see much of a use case for much more complicated data flow graphs where you would like to see a lot more distribution and a lot more complicated sort of interactions among the different subtasks?
Yeah, I've showed pretty simple ones here. We do have more complicated ones. As far as the runtime system, it handles it no problem. The data dependencies are respected and everything flows correctly. I'm not sure what your question is. Sorry.
So whether, if you have multiple cards or
Yeah.
multiple CUDA streams or so on, having those different tasks and then trying to take data out of each task and send it to a different card, a different stream or whatever is certainly more complicated, right?
It is more complicated, but it certainly is not an issue. It fits within the framework here. The framework is there. It helps if we have hints about where the critical path is. It helps if we understand more about the cost associated with the data movement and also the cost of the operation that we're going to do, how to do that scheduling. Those are all important things that will have to go into it. But it's no big issue other than that.
All right, well, I want everybody to along with me, thank Jack for being here in the theater today. Thank you again. And also, I want to remind everybody that we are recording these. So the recording of this presentation, including the slides, are going to be available tomorrow morning on our website. That's nvidia.com/SC13.